Good afternoon. So we move on from where we stopped in the last class. The last video, actually there was a cut in the last video, so I'll try to pick up from there. So we're saying that if you have a force of 5 Newton, for instance, a force of 5 Newton directed along the x-axis, that's in the positive x direction, and then if you want to get its unit vector from that force, you have to write the force this way. You have to write it as 5 Newton I. So if you want to get the unit vector from this, obviously you just need to divide the force, which is already in its vector form, by its magnitude, which is 5 Newton, and that is going to give you I, which is the unit vector in its direction. So something similar to this, or this is the way we actually came about the idea of unit vector in the direction of a vector. For instance, if you have some vector A and you want to get the unit vector in this direction, we say that the unit vector in the direction of A, usually denoted as A cap, is going to be equal to the vector A divided by modulus of vector A. You have learnt this in MTH 104. You have learnt it in physics, elementary physics. You have learnt it in mathematics, further mathematics at O level. So you should still remember all of this, but I think you understand what we mean by that by now. So if you observe carefully, that is exactly what we have here. We have the force F divided by its magnitude is giving us this. Okay, you can see everything we have done to arrive at this point. So this tells you that the unit vector in the direction of the force F is given by cos theta I plus sin theta j. Alright, so that is that about that. Anyways, okay, when we get to 3D analysis, you get to see elaborately how all these things can help us get our results, and by the time we begin to apply it into equilibrium of rigid bodies in 3D, equilibrium of particles in 3D, you get to appreciate all of these concepts better. But please ensure you understand them well now. Okay, I should like to say that the reason for these regular tutorial classes is not so much about you passing your exam. As a matter of fact, if the only thing you do is to attend revision classes that you will do, you will pass the exam. But I don't know what is passed to you anyways. But if you just want to pass exam, for instance, you can just attend only revision classes. Okay, practice a few questions, and you may be lucky enough they come out in the exam. The questions you practice come out in the exam and you pass. It's fine. But if you really want to understand, I think you should really want to understand, because even if you are not ever going to come across this in subsequent levels, which is very, very rare. In fact, if you are in civil engineering, computer science, you're in computer engineering, mechanical engineering, and all of that, you are still going to have to deal with something like this. Even in electronic and electrical engineering, you will deal with something like this. Maybe not applied to mechanics, maybe electronics and electrical engineering, where you do something analogous to this. So it's just good that you understand these things now. That is the essence of these classes, that you understand in details. You understand why we are doing everything. You should not just understand how to solve a problem, you should understand why you are solving the problem the way you are solving it. Okay, so that if you come across a situation where the problem has been twisted, you will know how to find your way around that. So that is the point of this whole thing. So please ensure that you follow properly. Okay, so that's the way it is. Yeah. Okay, so that is that about that. Then we said we should solve some problems on this so that you will know how to apply all of this. You know how to resolve forces, how to deal with components of forces in 2 dimensions. We want to get the resultant of more than 2 forces, that is 3 or more forces now, and you want to get the resultant. We've said it is just appropriate that you resolve each of those forces into vertical and horizontal components, then you add the corresponding components to get the components of the resultant, and from that you can get the resultant in magnitude and direction form, okay, as you should. Then also, in case you are given a component of a force, you should be able to get the force or its other components, okay, as the case may be. So depending on the situation depicted by the problem. Alright, so that is exactly what we should or be doing or will be doing in today's class. We solve one or two problems on this so that you understand. I'm just going to pick some specific examples so that you know how to deal with the two cases you can come across here. The first case is you can come across a situation where you are given a system of forces containing more than two forces and you're asked to get the resultant. Okay, then you can be given something like a force, maybe one of the components of a force, and you're asked to get the other component. Don't forget that we have dealt with how to resolve a force into components. Okay, it may happen that the components they are talking about are not rectangular components. That means the components are not perpendicular components. It may happen that they are at some angle other than 90 degrees to each other, and then that doesn't still matter. It simply means the component simply means when you add the component you get the force. Okay, so that's simply what it means, and that they can be at any angle to each other. Okay, so we look at those examples right now. So look at problem 2.21. Problem 2.21 says you should determine the x and y components of the forces shown. Look at the forces. You have the 424 Newton force, you have the 408 Newton force, and the 800 Newton force. You want to get the x and y components. Okay, that is quite straightforward. I'm not going to solve this for you. I'll just tell you what to do with a situation like this. Okay, look at this one. This 400 Newton force. What is it now? This 408 Newton force, for instance, you don't know the angle it makes with the x-axis. If you want to get its component along the x-axis, you have to find the angle it makes with the x-axis. So if you get the angle it makes with the x-axis, then its x component will be 408 multiplied by cosine of this angle that it makes with the x-axis. Okay, and so its y component will now be 408 multiplied by the sine of the angle it makes with the x-axis, or the cos of the angle it makes with the y-axis, and that component by our parallelogram rule is going to be facing downwards to be consistent with the direction of this. Okay, and in a similar manner, you look at the 800 Newton force. You will need to get the angle here. You can get that angle from this 600 and 800. Okay, so that means the length of this is 800, the length of this is 600. So you can get the angle it makes with the x-axis, and with that you can tell that its component along the x-axis is going to be 800 cos the angle it makes with the x-axis, where you will have obtained that already. So that's fine. You will get the x component directed this way. The y component will be directed upwards to be consistent with the direction of this and in line with our parallelogram rule. You can see something here. They have already established the parallelogram for you to show you that the parallelogram in this case is a rectangle, and to point out the fact that the components here are rectangular components, or to further drive home the point that the components here are rectangular components. Okay, so you do the same thing also for this force. Okay, but an interesting thing about situations like this where you have dimensions given instead of angles is that you know that this is 600. This from here to here is 600. You know that from here to here is 800, and you should have this stuff in mind, what we call the Pythagoras triples. Triple. That this is a right angle triangle, for instance. I mean, this to this and to this is a right angle triangle, and so if you want to get this angle, for instance, or you want to get the length of this side, if you want to get the cosine of this angle, according to your SOHCAHTOA, is adjacent over hypotenuse. Adjacent, what's the side adjacent this angle? Adjacent is this side, that's 800, over hypotenuse. Hypotenuse will be the length of this. You don't know the length of this, but you can find it from Pythagoras theorem. That will be square root of 800 square plus 600 square, or you use your Pythagoras triple if you know that offhand. 6, 8, 10 makes a Pythagoras triple, so the length of this side should be 1000. So because of that, if you want to get the cosine of this angle will be adjacent, which is 800, over hypotenuse, which is 1000, and with that you know what the cosine is. You will not need to get it in fractional form. It will just give you 800 over 1000. So this one will be 800 times 800 over 1000. So it's quite straightforward to deal with. I think that should be something like 160 or so. So when you do that, that will be the x component here. So in the same vein, you can get the y component. It's quite straightforward to deal with. Okay, I think I will let us resolve one of them so that you will see what I'm talking about. I will resolve this and get its x and y components. So I will expect that you are able to finish off the others. I mean for 424 Newton and 408 Newton. So I'll deal with this 800 Newton for you to understand what exactly I'm talking about with this. So we want to resolve an 800 Newton force into its x component and its y component. You're told that the dimensions are in millimeter, but it doesn't really matter anyways, okay, so far the dimensions are the same. Okay, all right, so we want to determine its x and y components. So let's quickly look at that. So we are told that we have this, so we have seen just now, we have something like this. This is the y-axis, this is the x-axis, and then we have a force, starting force of 800 Newton. This is the force of 800 Newton. Okay, and then we're given this rectangle. So that's this. Then we have this. We have this as our x-axis and this as our y-axis. So we have this as the origin shown in the diagram. Then this is 800 Newton force. So we're told that this length is 600. It is from this point to this point is 600, and this is 800. That's from this point to this point is 800. I have 800 right here. So that's that about that. So we want to get the x component of this force and its y component. So how do we go about that? So I said for you to proceed, you probably want to get the angle here. It's fine if you do. This is some angle theta, say. So from here you can say that the x component of this force, the x component of this force, if you are going to resolve this into the x-axis, can you remember how to resolve? You project from the tip of this a line parallel to the y-axis. So you go this way, parallel to the y-axis. So that's going to be something like this. So this is going to be the line. And then if you want to get the y component to project from the tip of this, a line parallel to the x-axis. So you go this way. This is the line parallel to the x-axis. And that is going to give you the tip of the y component. So the y component of this force has a magnitude, okay, depicted by this. And the x component of this force has a magnitude depicted by this. Alright, so this is the x component and this is the y component. Okay, we can call this the original problem has to do with three separate forces. So you can tag this F1 so that you don't mix them up while writing your answer. So you can call this F1x and F1y. Okay, so basically you know from what we have done so far that your Fx, F1x in this case, should be equal to 800, that's the force, multiplied by cos theta. Why is it carrying cos? Because it is the side, it is the components along the axis to which the force makes the angle theta. Okay, so we have seen that before. That's adjacent over hypotenuse, that's cosine. Adjacent to angle theta is F1x and hypotenuse is 800, this one that we have at this particular force. Okay, so if you want to get the cos angle, if you want to get cos theta, there are two ways you can do this. You can decide to find out what angle theta is first by looking at this. Now this triangle, this rectangle is similar to this rectangle. What I mean by that, this angle here is the same thing for both of them. Either you are considering this small triangle, you are considering this big triangle, it's the same angle for both of them. So we want to get your cos theta. You can say that you can find out the angle. You can say tan theta. Why am I using tan? Because I know this side 600 and I know this side 800, and I can see that for angle theta, this side is going to be opposite, because this side is opposite angle theta, and this side is going to be adjacent, which is also opposite angle theta. So I can say tan theta is equal to 600 opposite over adjacent, 600 over 800, and from here I can take the tan inverse and get my theta in degrees. Okay, it's fine. If you go that way, it's fine. So when you have obtained theta, then you substitute here and get your x component of this force. That is fine too. Now I don't want to do that because I feel that is not so smart a method to use, okay, because there are smarter ways to do this. Okay, so what I want to do, what I love to do, is to say that I know this side, I know the length of this side is 600, I know the length of this side is 800, so I can get the length of this hypotenuse, okay, using Pythagoras triple, or using Pythagoras theorem, as you may like it. So I can say that from that I know this side is 1000 from my Pythagoras triple. So because of that, I know that I can write out, I know that tan theta is 600 over 800. I can also write out that cos theta is adjacent, this is adjacent, 800 over hypotenuse, which is 1000 from your Pythagoras triple. If you like, you can check that. You're going to have square root of 800 squared plus 600 squared, so that's going to give you 1000. So that's the length of this side. Okay, so cos theta is going to be this 800 all over 1000, okay, or if you like 0.8. okay, so that's fine, it's okay. And you can also write out directly, because you know this side, you can also write out what sin theta is. Sin theta is opposite is 600 over hypotenuse is 1000, so this is 600 over 1000, so this is going to be 0.6. it's fine that way. So why have we done this now? So that when we need to use cos theta here, instead of putting in the angle, which can further give us some approximation error, of course usually negligible or insignificant approximation error, but it's just faster to have it done this way. So at the end of the day, because we already know what cos theta is, I'm just going to put this as fx is equal to 800 multiplied by cos theta. So my cos theta in this case is, as I already stated here, 0.8. so I have this to be 800 multiplied by 0.8. this is the same thing as 80 times 8. okay, so that's going to give you something like 640. so you have 800 multiplied by 0.8, so you have 640. so this is going to be 640 Newton, correct to 3 decimal places. That's our F1x. okay, so that's the x component of the 800 Newton force. Then to get its y component, F1y, obviously F1y is going to be 800 sine theta, because sine is opposite and this is the side opposite theta. This side is equivalent to F1y, so this is 800 multiplied by sine theta. So that's sine theta, as we already obtained, is 0.6. so this is 0.6. so I'm going to have 800 multiplied by 0.6, so that's going to give me 480. so from here I have the y component of this force to be 480 Newton. so that's that about that. So we already know how they are directed. So in this case, if you want to write your final answer, you can write that F1x, that's the y component of this force. You can say this is equal to 640 Newton. You can put it as plus 640 to tell you that it is in the positive x direction, or you can put it this way to say that this is 40 Newton and it's directed this way. This one 480 Newton, it is positive. You can write it as plus, just leave it this way, or you can state, or you can add an arrow to tell you that this is its direction. Okay, so that's not about that for 800 Newton force. So you can do something similar for the 424 Newton force in this question, and the 408 Newton force in the question. So That is quite straightforward to deal with. Okay, so this is a good example for cases where you have dimensions given instead of angle. So that these are the two ways you can approach it. You can either decide to get the angle, or you can just use the dimension directly. Usually more advisable when you know the Pythagoras triple. You can easily always check that with your calculator anyways. So that is that about that for this problem. So we'll pick another problem for you to understand this better. But please, you should have noticed that what we're doing here is just to apply all these things we have explained before. So if you still don't get what we are doing now, you probably did not get these explanations we have made before. So go over that video again if you still don't get this. Alright, so we'll move to another example now. So look at this problem now. Problem 2.30. Cable AC exert on beam AB a force P directed along line AC. You can see the line AC right there. Knowing that P must exert a 350-pound vertical component, determine A, the magnitude of the force P, B, its horizontal component. So look at the idea now. They said you have a cable AC, that's the cable. You can see cable AC right here. This cable AC, and it exerts on beam AB a force P. So you can locate the beam AB. This is the beam AB, and it exerts a force P on beam AB. Now it is not force Q. The force Q is just there, but we don't have any business with it. Okay, you can see it is not referenced. It is not referred to at any point in this problem, so you actually don't have any business with the force Q. Okay, so I said the cable AC exerts on beam AB. This is beam AB. So this is the cable AC. It exerts a force P directed along line AC. So the force it exerts on this beam, on this material, is directed along this line. Obviously, it should. We know that the force P, that's the force that exerts on the, must have a 350-pound vertical component. Okay, vertical component means components in this direction, in the vertical. Then also we want to use that information to determine the magnitude of the force P, because we know it's vertical component. We want to use that to determine the magnitude of the force, and then we want to find out what its horizontal component would be. Okay, so what's the first thing you need to note here? The first thing you need to note here is the fact that, I think I've mentioned this in the past, it is the fact that when you have a cable like this cable, the reason it can exert some force on this component or any of these components, because it is taut. I mean, by taut, I mean T-A-U-T. I mean, because it is under tension. You know, before you can, if you attach a rope to something, or maybe you attach a rope to this material and you want to use it to actually pull this thing upward, you know, this thing has to have it has to get to, you know, it has to be fully extended before it can begin to pull this material. Okay, so that's why that's what we mean by the rope being under tension. Okay, so when it is under tension, this is a general or universal case. When you have a rope under tension like the force it exerts on each point, okay, or the force is exerted at any point or on any point, is always directed away from that point. Please pay attention to the emphasis on away. It is always directed away from the point in consideration. So what is the point in consideration in this case? In this case, they said this cable exerts on beam AB a particular force. So where is the point at which it exerts a force on beam AB? It is the point A to which it is attached. So the force it exerts on beam AB will be directed away from the point A. That is, the effect of this rope on beam AB is that it gives it some support, okay, or it exerts some force on it, which is directed in this manner. I mean, directed away from the point A. It cannot be towards point A. That would mean that this is not supporting the beam, but it is actually pulling it, okay, further. No, pushing it away. So actually the point that is actually pulling it towards itself or towards the other point. So what I'm trying to say is that if we were to examine the force it exerts on the point C, it will be away from the point C. So that's the point. It's just like you have two idiots, one idiot at this point, another idiot at this point, and they are both pulling this rope. The effect on this idiot is that the tension in this rope, tries to pull him. Will that be push or pull now? Okay, tries to move these idiots towards this other idiot, while simultaneously it also tries to move this idiot towards the other idiot. And at the end of the day, who wins or where the motion will be is which of the idiot is able to exert the higher force. Okay, the higher force mean that this one will have to go this way, and of course at the same time this idiot also will be pulled backwards the same way, which tells you they are because they are under the same tension. Okay, so for you to actually have this idiot move away from this point, because this thing is already taught, I mean it is not ruled on each other, so this idiot also will have to move away. Okay, so that is the point. The tension for a rope, for a cable, what other weight can it come? You can have a rope without a cable, whatever they call it, is that the tension it exerts will always be away from the point in consideration. So for this point A, the force this cable exerts on the point A is away from this point A. So the force in consideration is the force directed from the point A towards the point C, and such that it makes an angle of 55 degrees with the vertical, as we can see here. So that force makes an angle of 55 degrees for the vertical. Okay, so we're going to draw what we call the free body diagram now for you to see what I'm talking about. Okay, so I'll produce the free body diagram right here so that you will understand how it works. So look at it carefully now. So this is the point. So this what we're talking about now. Look at this as an object. We have this object right here. We have this rope, or we call it a cable. Now we have this object. I want to move this object using this cable. What I mean by being taught is, now this in this case, when it is in this position, this thing is folded, this cable is folded. Being taut means that it has been stretched out, fully stretched out. So it is when it is fully stretched out that when you pull further, it is then under tension. That means it can now exert the force at the other end. When it was here to be fully stretched out, there was no way I could do this. So far it is yet to be stretched out fully, it cannot exert a force at this other end. That means it is still not in tension, and for it to be in tension it has to be fully stretched out. When it is fully stretched out and pull further, then it is under tension, then it can exert a force at this end. So what is the effect of this force now? So if this thing is stationed, okay, if this thing is stationed this way, and this also, look at my hand, is stationed like this. Now if this rope is under tension, that means it is fully stretched out and still exerts some pull further. Okay, the effect is that it is trying to pull this thing. The effect of this rope at this point is that it is trying to move this thing towards itself. Okay, but if I exert some force to make this stay, it will stay, but the moment I remove the force, it will drag this thing towards itself. So that's the effect at this point, the effect on this body at this point. So in the same vein, if this thing is under tension this way, okay, the effect on this is that it is trying to move this, okay, towards itself. Now why is this thing still positioned? Why is my hand here still positioned the way it is? It is because this thing, I have applied some force to stabilize it, to neutralize the tension of this one. Okay, if I release the force, for instance, by just releasing my hand, this thing would actually pull me towards itself. So the effect it has on this also is directed away from this point, just as the effect it has on this is directed away from this point. So that's why we said that whenever we are considering a point under tension, okay, due to the fact that it is connected to a rope, the effect of that rope or cable under tension is that it will exert a force along the rope or cable, but directed away from the point in consideration. So that's that about that. So we can now use this idea now to solve this problem at hand. So the problem says that we have this. So let me quickly make an illustration here so we can refer to it directly here. So we have a system like this, as you can see in problem 2.30. We have this, we have this right here. So you have a beam. You have a beam connected to this. This is the beam right here that we are interested in its stability. So we have this right here. You have this right here. So this is the cable. The cable goes this way to this way, and this is the point A. This is point B, and this is point C. So they said the cable is this cable AC exactly force. Now we've been told that this is at some angle to the vertical. They gave us that the angle it makes to the vertical is 55 degrees. So we have this point A. So they told us that the vertical component of this cable, the tension in this cable, or the force this cable exerts on this beam, is 350 pound vertical component. So with that, we want to get the magnitude of the force and its horizontal components. Okay, so how do we go about that? The first thing is to produce a free body diagram. So this is the question. So we'll produce a free body diagram. I'll have to do that here so that we can look at both simultaneously. So in your free body diagram, we are only interested in the points that have to do with the problem at hand. You can see I've intentionally missed out these points. Like in the diagram, we have some force Q here. There's no reference to the force Q or the point where it is acting in this problem, so we can do well to ignore it. We don't have any business with it in this case. Okay, so we face what we have business with. So in this case, we have the point A, so we indicate the point A. This is the point A we have business with. We have the point C, we indicate the point C we have business with. That is everything. That's all. We don't even have any business with point B. So we just extend this, extend this, extend this. Why do we have to do this? Because we need the direction of the force. So extend this also. Then for this, okay, I can also draw a dotted line to show this. But then I know that what I'm interested in is the force exerted at this point, and the force exerted at the point A, and it should be directed away from the point A. So that force should be directed this way. Okay, you can draw it in ways like this. So this is the force we're interested in, some force F. Then we know that this force F makes some angle 55 degrees to the vertical. We indicate that. Okay, so we want to resolve this force into vertical and horizontal component. This is the horizontal, this is the vertical. Vertical is here. So we can get its component by extending this. For instance, from the tip of this, we can extend to parallel to the vertical, okay, so as to get the horizontal component. So the horizontal component will be directed this way. This is the horizontal component. To get the vertical component, we can extend from the tip of this parallel to the horizontal. So when you do that, you're going to get this, and then from here we are going to get our vertical component. So this is going to be the vertical components. Okay, so with this we are good to go. We already know what the force is like and then what its components will be like. Okay, so the horizontal component is Fx and the vertical component is Fy. So we know this angle is 55 degrees, and that's the angle it makes with the vertical. Obviously that's the same thing as this angle, 55 degree. What do you call that? Corresponding angles or alternate angles, whatever. So you know the angle it makes with the vertical, this is the vertical and this is the vertical, so it's 55 degrees. Alright, so with this we are good to go. Or if you like, you could say it makes an angle of 90 minus 55 degrees here, considering this right angle triangle. Anyhow you say it, you're still fine. So this point A, this is the point C, this is the point B. Alright, so with this we are good to go with our analysis. Okay, so having produced this free body diagram, we will now state that the x component Fx is actually equal to F sine. You know why it is carrying sine now? Because we want to use 55 degrees, and 55 degrees is not the angle it makes with the x-axis, it is the angle it makes with the y-axis. So this one is sine 55 degrees, and then Fy, F subscript y, is going to be what? F cos 55 degrees. So we know this from what we have done so far. Then going further, we have it that we have been given that the P, the force P, has a vertical component which is 350 pounds. So they already told us that our Fy is 350 pounds. So we leave it like that, 350. So from here we can get our F. So from here it means that, okay, so that's the first part. The first portion of the problem says we should find the magnitude of the force. That's F. So our F from what we have done here is F is going to be equal to 350 divided by cos 55 degrees. So from here we get our result. That will be the magnitude of the force F. Okay, this thing is in degrees. This is radians, so we'll change it to degrees 3. So from here we can get our result, 350 divided by cos 55. So that's going to give us 610. So that's okay. So the force is actually 610 Newton in magnitude. So that's the magnitude of the force. Alright. So the second part is we should obtain, what is it now? We should obtain the horizontal component of the force. So the horizontal component, that's your Fx. So you know what to do with that. Continuing here, this is part B. Okay, so continuing here, we have Fx is equal to, as we have obtained it here, it is F sine 55 degrees. Okay, it's fine if you put 610 directly, but to avoid some approximation we have done here, so as not to carry the error into this, I can use this directly. So I'm going to say this is equal to F sine this, and this is going to be 350 divided by cos 55 degrees, then multiply by sine 55 degrees, sine 55 degrees. Of course, that is the same thing as, you know, this is sine 55 degree over cos 55 degree, which is tan 55 degree. So I can put this as 350 tan 55 degrees. So from here I can get my f sub x. So that will be 350 sine 55. So I'll get 286.7. So in three significant figures, that will be 288 pounds. Sorry, this is pounds. The problem is given in pounds. So this is going to be 288 pounds. So that's that about that. Alright, the question is very clear. It says you should get the magnitude, so we don't have to put it in vector form. You don't have to indicate direction. And then they wanted to also get the horizontal component. You also don't have to indicate direction. Okay, so your diagram suffices for the specification, or for specifying the direction. If anybody needs to know the direction, they will already see that in your diagram. So I guess that is that about that. Okay, so we will stop there. So what I need you to do is to attempt all the other problems we have in this section we just treated. So ensure that you try your hand on all the problems that will be, or those are problems from 2.21 to 2.42 to 2.42. So attempt all of them, please attempt all of them before our next class next week. So if you have any issue with any of them, if you have any issue with solving any of them, resolving any of the forces, or interpreting any of these problem statements, then you let me know on the group, so that I can pick that particular problem and address it in the next class before we move to the next section. So I guess that is that about that for now. Thank you for your interest in Max Engineering tutorials. Hopefully things will get better and we will resume before the end of the year.